Welcome to the Frenetic webinar. I'm Ines and I'm part of the marketing team here. We are very excited to start this series once again and to bring in speakers who are experts and are going to be able to teach you things about different topics in power electronics. Our goal is to host one of these webinars around once every 2 months, and they will also be uploaded to our YouTube channel along with all of our previous webinars. As you may already know, we just recently launched Frenetic Factory, which is our step forward from simply having a design software to now using our algorithms to design and manufacture your components. And if you would like to learn more about that, you can check out our LinkedIn page or go straight to our website at frenetic.ai. Today's speaker is Jonas, our CTO of Magnetics and professor at HSLU in Zurich. And this presentation will be on the effects with considerable impact on core losses. So without further ado, Jonas will now take over.
Thanks again for the introduction. I will now start sharing my screen. That was the wrong screen. Here you go. Can you see the screen now?
Yes.
All right. Okay, so today's webinar is about effects with considerable impact on core losses. It's kind of a follow-up on the seminar I held, 3/4 years ago, where it was more the basics about core losses. Now we go a bit more into detail. The structure of the presentation is I will give a first general introduction about what type of core losses are there, and then I would like to go into more details and have three effects or discuss three effects that have a considerable impact and are usually overseen by engineers or often overseen by engineers. Let me start with the basic principles about core losses. Very generally, you can say that there are three kinds of core losses in magnetic materials. One is the so-called hysteresis losses. What are hysteresis losses? So if you magnetize a magnetic material, which can be well represented by a BH curve, even if you do this magnetizing very slowly, ramping up and down, even if you go almost infinitesimally small ramping up or down, you will still have a certain area of this loop, and this area represents core losses at the end. Why is this the case? The reason is that a magnetic material, a ferromagnetic material, is usually magnetized in so-called domains. So it's split in domains. Each domain is magnetized. However, the net magnetization from outside seen is zero. Only if you apply an external field, you will see that the domain walls are shifting a little bit, as you can see here on the right picture. And this leads to a positive or negative net magnetization. However, these domain walls are not shifted very smoothly. They are the so-called Barkhausen jumps, lead to very abrupt changes of these domain walls. And because of these very abrupt changes, you have a very strong local field within the material, magnetic fields, which lead then to local eddy currents, and this leads to core losses, and this cannot be avoided. Depending on the materials, these kind of losses are a bit higher or lower. This is one type of core losses. It's also called static because it's happening even if you have a very low frequency. Another type of core losses are the so-called eddy current losses. They are dependent on the material conductivity and core shape. They are illustrated here. If you have a flux through a magnetic material, as shown here, and this flux changes with time, you will induce an electric field, and this eventually leads to so-called eddy currents, and these eddy currents are flowing in your material and leading to resistive losses. Now, if you cut the materials into sheets, or as shown on the right picture, you can reduce these type of eddy current losses. However, you can never get completely rid of those. They affect the BH loop as well, so you can see them. Here on the right bottom picture is a little plot shown where it's a material with isoperm 500F in this particular case, where a rectangular voltage waveform has been applied to the core, and this leads ideally to an ideal triangular current waveform, as you can see here. However, what you can see here is that the waveform has kind of an offset. When ramping up, it's a positive offset. When ramping down, it's a negative offset. If you see something like this, it's very typical for eddy current losses. A third loss type basically is just the sum of all other effects, so-called residual losses. And here is a very an example where you can see how they affect the BH loop. Generally, you can say that you have a BH loop as shown here. You put, again, a certain waveform to the core. It doesn't have to be like here. This effect happens all the time, but in this case, you can see them quite nicely. You ramp up the material, you ramp up magnetization, so you magnetize the material. And then at some point, you abruptly stop the magnetization process. And then the material should stay in this position. However, because this is a physical system, it takes a bit time. So-called relaxation processes take place until the material actually is in the place it reached this new thermal equilibrium. Think of it like a spring. If you pull a spring very quickly and then stop the spring, still the spring will oscillate a bit until you reach a new steady state point. This can be seen here. After that, a normal demagnetization process happens between 3 and 4, but this is not what I'm talking about. It's really this short period here, 2 and 3. I'll go into more details later during this presentation. So if you can describe all these 3 loss types, you basically have a perfect core loss model, but this is not so simple. What is commonly done to model core losses? A very famous equation most of you are probably aware of is the so-called Steinmetz equation. It's quite old. It has been derived for sinusoidal waveform excitations. Basically tells you if you increase the frequency, the core losses are not, let's say you double the frequency, the core losses are not doubling, they are increasing with a higher factor because of some nonlinear effects, which can be represented with a parameter alpha, the same for the flux density beta. Now, this equation has been improved in certain steps, and at some point, kind of a standard appeared. It is called the improved generalized Steinmetz equation. The core idea, it looks quite complicated, forget about the parameter, but the core idea is the losses are not really a function of the frequency, but they are a function of dB dt, so how fast you ramp up or down the flux density, as well as delta B, which is the same as here. The parameters are such that they are, again, alpha, beta, and k. Ki has to be calculated as a function of k and the other parameters. If you put a sinusoidal waveform into this equation, you end up here. So these are kind of the basics about core loss modeling. Now the question we asked ourselves is, well, how suitable is this improved generalized Steinmetz equation for typical power electronics flux waveforms? And here is a kind of a list of very typical waveforms you have in power electronics. Sinusoidal waveforms, or you have a DC current with a high frequency ripple. This is typical for buck boost converters, for instance. Non-sinusoidal AC currents, what you can see can be, for instance, in a dual active bridge, or in a PFC, you have a waveform like this, a sinusoidal current with a high frequency ripple. And the rest of this presentation, this was kind of the introduction, is we analyze these waveforms and we show 3 effects that have a considerable impact on core losses, which are typical in these kinds of waveforms, but that are not covered by the improved generalized Steinmetz equation. So basically, these are 3 isolated stories that will be form the rest of this presentation. One example of an effect affecting static hysteresis losses. It's the DC bias effect. One effect playing in the domain of eddy current losses. It's I call this here orthogonal flux, and one effect, relaxation effect, which plays in the residual losses. So the rest of the presentation is first I talk about the DC bias effect, then about the relaxation effect, and then about orthogonal flux. This will then conclude the presentation of today. So the first thing one observes is if you have a, let's say, a current waveform like this. This is the current in the core under test at the voltage across the core under test. And let's say this current here has a certain DC bias current. Now you remember the fundamental equation that we are analyzing is this improved generalized Steinmetz equation. I put this here on the bottom left. And you can see independent of IDC, the DC part doesn't play a role in this equation. So doubling IDC or should not affect my core losses. However, we did quite some measurements. You can see here that if I have an IDC, which can be translated in the magnetic field strength DC part component, which is directly proportional to IDC. If I increase my IDC from left to right, from 0 to, in this case, 60 amps per meter, the core losses increase. Depending on the operating point, it looks a bit differently. You see here, these are different operating points, different delta B. The frequency is always constant in these cases. Now, another analysis has been done where we change the frequency. We have here 3 operating points. The blue one is without a DC magnetization. The green one is with a DC magnetization. The same for here, red, no DC magnetization. And this turquoise is with a DC magnetization. And you can tell that again, you see the effect of a DC magnetization leads to quite substantial higher losses. However, the factor by which they increase is kind of independent of the frequency. In other words, it's independent of the frequency means it's part of this static hysteresis losses, right? It doesn't, the frequency doesn't play a role in this consideration. Here, the same. Basically, these pictures here are translated and normalized. You see here the losses with DC magnetization over without. So basically how much the losses increase under certain operating points for as a function of HDC. And you see that the losses can increase quite substantially up to a factor 2 or even more, depending, of course, where your operating point is. Reasonable operating points are somewhere here between 30, 40 ampere per meter, but still the losses can increase by a factor of 2, something we should not neglect when designing magnetic component. Going back to the initial figure, we see here the implications to power electronic systems. These are the typical waveforms in power electronics, very typical for buck boost converters, as shown here. You have this DC magnetization, or also here, when you have a high frequency ripple over a low frequency current, you have these so-called major loop and minor loops in the BH curve, and all here, they are all affected by a DC premagnetization. Each of these minor loops is affected by a DC premagnetization. Now, how can you take this into consideration? Basically, there are 2 ways of doing it that we are aware of. One is the so-called, well, this is something we derived at that time when we did this analysis, is the Steinmetz premagnetization graph. It basically tells you how the Steinmetz parameters change as a function of the DC premagnetization of the magnetic field strength. So basically, if you have, let's say, this case, you go calculate the HDC here. You use the Steinmetz or the improved generalized Steinmetz equation. However, instead of using the known parameters, you go read from this graph, where are your HDC, where you are. And in this example, for instance, you multiply K by a factor of 1.2, or you multiply beta by a factor of around 1.85 or something like this. Unfortunately, we were a bit naive when we derived this graph. We hoped that then the manufacturers would add such a graph to their data sheets. That never happened. So it's kind of it's not so easy to have access to these graphs. For certain materials, they are published, but yeah, it's not so straightforward to use. Another approach is shown on the right side. That's basically how we are doing it at Frenetic. It's basically we have a material database where we have different material pre-measured data, and from there we get the parameters and use then the standard improved generalized Steinmetz equation. The right part, I will come back to that a bit later. Well, I have to be a bit more accurate. We are going to do this at Frenetic at this stage. It's not considered in our analysis software. So is this a problem we have only in ferrites? No, this happens in ferrites a lot. You have the impact on losses. We tested N87 and N27, so different type of materials, as you can see here. And the impact on losses is quite high. It's also the case in silicon steel or nanocrystalline materials, but in powder cores, for instance, we observe that this effect is negligible. Yeah. So with this, I conclude the first part of this presentation. At this stage, we are also trying to, or we are conducting research to better understand this effect. So far, I only described how the effect is manifested, but not why this effect happens. And we are conducting research to better understand this effect and hopefully derive a new approach that allows us to actually take this into consideration in an easier way, like to derive a new model that allows us to take this effect into consideration. Okay, so this was the first story of today. The second story is the relaxation losses. So a waveform that is typical in power electronics is something like this. It's for instance, in a dual active bridge, you have a waveform where you have some phases of constant flux, then you have a change in flux, again constant, and so on. Now again, we go back to the improved generalized Steinmetz equation, and we think, well, what kind of losses would you expect based on this equation? And you can say, well, you have losses in the part when the flux ramps up or the flux goes down, but you will not have core losses in the phase of constant flux as shown here or here. Now we did again measurements, and some results are shown on the right side. What we did here is, what you see here is not the power loss, it's the loss energy per cycle. So basically it's only this integrated part without dividing it by the 1 over T or by T. And what we could observe is that if you increase T1, so you increase the phase of constant flux, the losses increase. So at the beginning, let's say you ramp up, your loss contribution was up to here, but then you keep the flux constant for, let's say, 10 microseconds. And in this 10 microseconds where the flux is constant, you still have a loss contribution, which here is shown in microjoules, so the energy part of it of around 2 microjoules or something like this. So it doesn't mean that the core losses increase when you increase T1, because the frequency also drops. However, the energy per cycle increases. Why is this the case? I mean, this is a phenomenon that's known in literatures. People studied core materials for quite some time. What happens is, if you ramp up the core material, basically repeat what I said at the beginning, you ramp up the core material up to a certain point and then abruptly stop the voltage or put the voltage to 0, still something happens to the material. The material did not yet reach its thermal equilibrium, so that you have some relaxation processes, and it takes some time until the core goes back to its thermal equilibrium. And from there, well, you have a normal demagnetization because you have some resistive parts in your circuit, but this time from 3 to 4 is much bigger than 2 to 3. It's shown here on the right side. You can see the time domain current waveform. Basically, you ramp up very quickly, then you stop, you put 0 voltage across the device, and relatively quickly you reach this thermal equilibrium, and then you have a expected demagnetization because of some resistive components in your circuit. So it's quite interesting, and something that affects from this drop here has a big impact on your, or can have a quite substantial impact on your core losses because the area of the loop increased. Well, we did quite some measurements and try to model this effect. Basically, what you can see here is the plot again. We saw that independent of the operating point, so independent on how fast and how far you ramp up or down, the delta, the speed, how fast you reach equilibrium is the same, or almost the same. So you can conclude that we call this tau, like the how long it takes to reach equilibrium is constant, independent of the operating point. So what we have to do is, in order to model this, we only have to determine delta E, right? How much energy in total would occur maximum. If you know that, it's a function of delta E times 1 over, that's just the exponential behavior of this curve. Tau is constant. And basically the question, depending on how long you keep T1, you have more or less energy contribution to the core losses. Now the question was how to determine this delta E. We did quite some measurements with different operating points. Here, this is a function of dB/dt, like of the x-axis, and here on the y-axis is delta E. Why is it twice delta E? Because in our measurements we have it here. So one contribution here, and then on the, if you come down again here. So it's just per cycle you have twice this contribution in this type of waveform. And you can see that the curve looks like this. I will come back to this, quite important. It's a double logarithmic plot, and the curve looks like this. And the same is if you have on the x-axis delta B, it's again approximately a straight line in a double logarithmic plot as here. Now, if you have a double logarithmic plot and you have a straight line in a double logarithmic plot, you can conclude that this is following a power function. Well, that's now maybe not so clear what this means, but basically it's the same behavior as the Steinmetz equation behaved. You have a certain parameter to the power of another parameter, parameter to the power of another parameter. So basically, delta E is a function of how fast you ramp up, dB/dt, and what is the total, like delta B, you go from bottom to top. And we introduce these new parameters to describe this. For each material, you will have these parameters, and they allow you then to determine delta E. Basically, what you can see here is this is the first step of our modeling approach. Again, looks a bit complicated, but if you look in this a bit more detail, it's not super complicated. This is just the improved generalized Steinmetz equation. Didn't change as the initial, the first equation I showed today. But for every time you move to put 0 voltage across your device, you add a certain loss components, and these loss components can be calculated based on the two equations I just explained. One is this power function, and the other is this exponential behavior. So the right part basically describes this part, and the center part here describes these curves here. Okay, but this still not super useful because, I mean, okay, you have often this type of waveforms, but not every day, right? It's something, well, it's very specific case. We wanted to generalize it. And the idea is to have to be able to consider relaxation losses also in triangular waveforms, which are much more typical in power electronics. And the thought we had is something like this. If the D, so the duty cycle, is around 50%, it's a triangular waveform, then most likely the improved generalized Steinmetz equation works quite well. Also because it's usually measured or trained, like it's usually fitted with this type of waveforms. However, if you go to very low duty cycles, let's say you ramp up very quickly and then have a phase where the flux is not constant but slowly decreasing, then you probably underestimate your core losses. And the same, of course, if D is close to 95%, you have the same effect. So the hypothesis was, okay, your losses in this kind of waveform are probably between the losses that IGSE, improved generalized Steinmetz, gives you, and IGSE plus the full contribution, so this delta E we calculated before. So you most likely, or the hypothesis was you are in between these two curves, taking relaxation losses to the full and completely ignore them. These are the two equations. And as we are expected, you see here the different operating points. If you go D close to 0, you're much closer to the upper loss limit. However, when you're close to 0.5, you're much closer to the improved generalized Steinmetz equation. So this was confirmed. Now the last part of this equation was actually, well, we need kind of a fitting of this curve, right? So we need an equation or another parameter that is for D0 should be close to 1, right? Because when you're at 0, you would like to take the full delta E into consideration. And for D, duty cycles close to 0.5, it should be 0 because you don't want to include the relaxation losses here. Now there is an equation that nicely describes this. We found an equation that fits well this behavior. It's shown here. And basically, it's a function of how fast is the dB/dt before and after the point of flux or voltage change. And this can be as a function of the duty cycle written like this. Again, you need a new parameter to describe this. But all this led then to something we called, maybe it's a bit ironically, right, the I² GSE. It's the improved generalized Steinmetz equation that allowed us to fit this curve these points quite nicely. Now, I know this might look a bit complicated. However, if you think about this, it's, let me try to show you how one could use this kind of equation. So basically, the improved generalized Steinmetz equation, still the same equation as at the beginning, is evaluated for each piecewise linear flux segment. And it suits very well for that. However, it ignores the effect of relaxation, and this effect of relaxation always happens when you have a voltage step, because when you suddenly change the piecewise linear flux segment's direction, then you have certain effects and they are ignored. So for this, we add a new term, which basically for each voltage step, you use this term. You evaluate this term. This part here analyzes how big is the effect, and this is basically for how long you have to consider it. Yeah. So these are the two equations I've shown before. Okay. So of course, a bit self-critical. You need 1, 2, 3, 4, 5 new parameters, and it's not so easy to measure them, but it's possible, and you can automatize. You can have a core loss setup that automatically determines these parameters, but it's definitely not something you can do in an afternoon very quickly. But I think it also the whole work around this work here also helped to understand core materials better. Okay, so that was the second story. So first story was about DC magnetization, the effect of DC magnetization. The second part of today's story is relaxation effect, how they affect core losses. I go now to the third and last part of today's discussion, and it's an effect that we see in tape-wound cores. Now, what are tape-wound cores? Tape-wound cores is usually, or you know them under the term amorphous or nanocrystalline materials. However, they are called tape-wound cores because how they are built. They are basically, I don't know, a tape wound up, as you can see here. Or here is a photo of one of these cores. What's the advantage of these cores is they have very thin ribbons, and because of this, they have very low, eddy current losses. Now, if you have a flux from left to right or right to left, so along the tapes, the losses are quite small because of these thin ribbons. There is almost no path eddy current can flow. However, they have, in certain circumstances, higher losses than one would anticipate. And I would like to give you two things we could observe in the laboratory. One is, often they are wound like this, and then cut in two in order to be able to provide an air gap. Let's say if you build an inductor. Now, if you just cut these devices, what you get is in the process of cutting by machine, you introduce short circuits. You have to think all these 20 microns, very thin tapes, cutting like this, suddenly they lead to short circuits, and you can have eddy currents that are flowing as shown here. So the room for eddy currents to flow is actually quite high at the edges of the cut where it has been cut. And we could also show that if we put this then in a ferrite chloride, so a certain material that took away these short circuits, the core losses substantially was removed. And by this, we could kind of confirm that this effect really happens. And we also know that certain manufacturers let's say in a positive way, a good manufacturer, I believe, has this under control and can avoid this kind of effect. And by this, you don't have these additional eddy current losses. But if you go for a very cheap manufacturer, you might see additional losses because of this cutting or bad cutting process. Now, there is another effect, which is much more problematic because it cannot be avoided. And this is shown here. So what you see here is this tape-wound core. You see the little ribbons here. We have these eddy currents because of short circuits, but let's ignore them for the moment. Let's only look at the upper point here. If you have an air gap, you also have a fringing flux, as shown here. Now, this fringing flux has an orthogonal part to the ribbon. Now, here, there is nothing that kind of stops the eddy current to flow, right? It can nicely flow in the ribbon. So basically, if you have an orthogonal flux to your ribbon, you will have very high current losses, eddy current losses. And this is something, well, the only way of avoiding this is not having an air gap or having a very small air gap. This we could also confirm in the laboratory that this effect really happens. We took this C-shaped cores as shown here. Once we did a horizontal displacement, and what you can see is that let's say we did a horizontal displacement and a vertical displacement. If you do a vertical displacement and the flux lines point like this, there is no orthogonal flux to the ribbons. And because of this, you have kind of no increased core loss. That's shown here on the lower picture. But if you have a horizontal displacement as shown here, the core loss may substantially increase. So this is something very difficult to control. Of course, you don't do that, but what you have is an air gap potentially, and then you will have additional losses. Or another case, if you build a transformer, now this is a transformer, but not a very technical transformer. It's just a laboratory setup to prove, to show what happens. You have a primary winding, a secondary winding, and a very high leakage flux here, or leakage path. Now the primary winding leads to a flux like this, plus one part is not going through the, well, I miss secondary winding, primary winding. So let's say I have a current in the secondary winding. A part of the flux goes through the window, which is usually called the leakage flux. At this flux part has an orthogonal path through to the ribbons, and by these higher core losses. You can see here the results. You have this increased secondary current, which in an ideal transformer would not lead to increased core losses, but in a transformer with high leakage flux, the leakage flux is orthogonal to the ribbons, and you have a very high additional core losses here. Okay, so these are effects that happen, and this is not something very new. I mean, this is a relatively old publication that we found that describes exactly the same. You can see here the effect amorphous core, or this material here, how the core losses increase. However, in ferrites, they remain more or less constant. And the reason they describe here is exactly the same. It's the orthogonal in-plane eddy, or orthogonal flux lines, or in-plane eddy current losses, how they describe it. Okay, so this kind of concludes my talk today. I would like to conclude it by, well, first, we have three effects. How that's kind of a qualitative or a rough guess I made. How much are core losses increasing because of these effects? And I think for a DC bias, you can say up to 100% relaxation. I don't think it's super problematic, maybe up to 30%. However, in orthogonal flux, if you have non-gapped in a transformer, maybe you have up to 50% loss increase, gapped, maybe up to 300% increase, because here the effect is very good. Don't say these numbers are not super exact, but it's a rough estimation based on all these analysis we did. Now, the question many of you might ask yourself is what to do. Well, I think the DC bias part should be included in modeling. The relaxation effect, I think it's okay if you just be aware of this. Would be nice to include it in modeling. Maybe in the future we will have models that are able to model this in a easier way than with additional parameters. And the orthogonal flux, I think you should, this is very important that you're aware of this effect. You should have a wise selection of material, which doesn't say you should not use amorphous or nanocrystalline materials, but you should use it when this effect is not super dominant. And I think you should also avoid a gap. And that's something researchers are working on. In order to be able to avoid a gap, what they try is to reduce the μr, so the relative permeability of this material, because people are aware that a gap in these kind of materials is problematic. Okay, I hope I could, I hope it was interesting to you. I think we have now time for Q&A, but I will hand over back to Ines. But my part is, I'm finished for now.
All right, thank you, Jonas, for your presentation, and thank you everyone once again for joining. Does anyone have any questions? You can ask them in the Q&A or in the chat. We'll wait a couple minutes in case anyone does have a question. Oh, we do have a question. Are you able to read them, Jonas?
I'm able to read them, yeah. So the question is, how did you estimate the core loss for the converter? Not sure if, like, I go back to this slide here. So if you have a converter, what you do is you usually do a simulation in a circuit or something like this, and you end up with a waveform like this. And depending on the waveform, you calculate core losses based on these models that we were shown. Now, I think the best case of how doing this is if you, let's say, take the most complex waveform as shown here, you cut this into piecewise linear segments. And for each piecewise linear segment, you apply this improved generalized Steinmetz equation. Plus, for each turning point here, you add the relaxation part. Now, I said this is not so easy, so maybe this is not super critical if you cannot do this. However, by calculating the core losses in this piecewise linear segment, you should also consider the DC bias. And like this, you will get quite accurate core loss calculations at the end. I hope this answered the question. If not, happy to follow up. I will now go to the next question. Yeah, how do you handle thermal and mechanical stress effects? Are there any aging effects? This is a very good question, and we are aware that if you have mechanical stress or thermal stress to the components, that this will increase the core losses. So, however, at this stage, I cannot say much more than that would be a fourth effect here, and we are conducting research or planning to conduct research to actually learn more about these effects. At the moment, we don't consider it. I hope I will give another webinar very soon about mechanical stress in the context of core losses. Now there was another question. I think this is related to the first question. I was asking about the core loss plot that you showed in one of the later slides before conclusion. Yeah. Maybe we can follow up on this question later. I'm not sure which slide and to which topic you're referring to, but maybe you can ask again and I can come back to that. Like if you tell me which of the three effects, and then I will go to one of these core loss plots. Now the next question is how to get the Steinmetz parameters for different core materials. Are there any better sources of data than the datasheets of the manufacturer to calculate them? I don't have a very good slide here where this is shown, but basically, I mean, the Steinmetz equation is an empirical equation. So basically, you need to have measurement results in order to get these Steinmetz parameters. Now, the easiest way, of course, is to use data sheets from core material manufacturers. And what you need to have is it's basically three unknowns, K, alpha, and beta. So you need 3 operating points. And with 3 operating points, you're able to fit or to determine K, alpha, and beta. If you don't know how to do it, I'm happy if you send me an email. I can quickly show you. It's not super complicated, but it's basically this. Now, are there better data sources? Well, if you measure core losses yourself, that would be much better. Maybe there are some other databases available online. Yeah, but the easiest is data sheets. So I think like this. the question is, does leakage inductance affect the core losses? Not directly, except of the case here. So if the leakage inductance is big, it means you have a high path where orthogonal flux, or how they call it, in-plane eddy current, can occur, and then you have higher core losses. But let's say if you have a ferrite material, that's not a problem. Then the next question, talking about Steinmetz equations, are they valid in any operating condition? Yeah, high frequency. That's a very good question. This is a bit linked to this initial discussion I just had. It depends. You go to the data sheet, you take 3 operating points, and you get K, alpha, and beta. Now, if you get these 3 operating points, let's say at 1 kilohertz, your Steinmetz parameter will not be very accurate for 200 kilohertz, let's say. So you have to do this curve fitting in the operating range you're interested in. But if you do this, then that's not should be okay. So whether the Steinmetz equation is okay at high frequency depends mainly how you how you fit the parameters at which operating points. You have to then also choose high frequency operating points. Now, having said this, there are some other effects happening at very high frequencies, which are not covered by the Steinmetz equation, like dimensional resonance, eddy current effects, if you have very big core sizes, things like this. So at some points, very high frequency, the material this equation might not be good enough anymore. Okay, I think these were all questions. Is the Frenetic tool more accurate than using Steinmetz equation and curve fitting? Yes, I think the Frenetic tool is more accurate because of different reasons. First of all, because we measure core losses, we have better data embedded. We also not use the standard Steinmetz equation. We use the improved generalized Steinmetz equation, and we are working on having a database like as shown here, where we should have an even higher accuracy.
All right, I think that was all the questions. So thank you everyone again for joining. We hope you learned a lot from today's webinar, and you will receive an email tomorrow with the link to rewatch it and with more information about our production capabilities. Feel free to either contact Jonas or me for any other questions, and we hope you have a great rest of your week.
Thank you very much also from my side.